So today we're going to take a look at section 4.4, a closer look at reactions, particularly redox reactions. Let's review our state symbols. So here we've seen this equation before. Let's just go back and review it. A is referring to the compounds to the left of our arrow in an equation. Those are called reactants. B is referring to the compounds to the right of our arrow in an equation. Those are called products. C is referring to this state of matter, AQ, which is aqueous, which stands for something dissolved in water. D is pointing to L, liquid. E is pointing to this 2 down here, which is our subscript. F is pointing to S, which is our solid symbol, state of matter. G is pointing to this whole number in front of our compounds, which is called a coefficient. And H is referring to this arrow, which is the yield produces sign. So the states of matter, like we have seen, are written in a chemical reaction as subscripts next to the compound. L stands for liquid, AQ stands for aqueous, S stands for solid, and G stands for gas. If water is produced in a reaction, we write water as L. If a solid is dissolved in water, we write it as AQ, and a precipitate is written as an S. Let's take a look at double reactions more closely at the atomic level, and this is going to be our beginning of ionic equations. Now, before we get started, the word ionic looks like, or has the first three letters. The first three letters of it are the words, or is the word ion. So in an ionic equation, which we're going to be taking a look at today, it will involve the writing of ions in some sort of equation, just to kind of give you a little trick there, okay? So double replacement reactions. We have a aqueous solution of AgNO3. What aqueous means is that the Ag and the NO3 are separated into their ions. So you have Ag ions floating around with NO3 ions. Okay, that's what aqueous means. It means that they're just floating around separately, happy in this water. Over in the beaker on the right, we have KClAQ, which means it does the same thing. You have these K ions and you have these Cl minus ions that are sort of floating and swimming around, just doing their own thing. Okay, all the reactants are in ion form because they are in solution. Anytime you see AQ, what that means is that it means that the two cations and anions are broken into their positive and negative components. Okay, because the water basically pulls them apart into their ionic form. So what we can do is whenever you have an aqueous solution, you can write out those ions separately in their ionic form. So you would separate Ag and NO3 into their two ions that make it up, Ag and NO3. Where did that positive and that negative one come from? Well, it's sort of like the reverse drop and swap. Ag, you know that if it's with NO3, has to have a positive 1 charge, and NO3 would have to have a negative 1 charge. So you're basically just writing the oxidation numbers of the aqueous solutions. So KCl, because it's aqueous, and again, this is only if you have this aqueous part here, you can separate it into K positive AQ and Cl minus AQ, because basically before they are mixed together, all four of those ions are just sort of separate, floating around. Okay, so then we're going to take these two beakers and we're going to pour them and mix them together. What happens when Ag and Cl are mixed? Well, if you remember that solubility table, if you look, you will see that AgCl makes a precipitate. It makes a solid. So the AgCl would form a solid and settle to the bottom. And the KNO3, if you remember also, the nitrates always form aqueous solutions, so nothing happens to them. So the NO3s start as ions and they stay as ions because they are aqueous. And the K ions from this guy stay in solution here. So the only unique thing that is happening is that this Ag and this Cl are reacting together to form a solid precipitate. Okay, so when we write an ionic equation, what we are going to do is we are going to write only the parts of the equation that go into making the precipitate. So for example, we have these as our reactants. These are all the reactants in their aqueous ionic form, and they are going to make AgCl solid, and then the K ion is going to stay as an ion, and the Cl minus ion is also going to stay as an ion. So here is how you come up with an ionic equation. If the ion appears aqueous on both the reactant and product side, we're actually going to cross it out. So K plus AQ appears as K plus AQ there, and Cl minus AQ appears as Cl minus AQ here. So we're going to delete those, and then whatever is left, we are going to write as our ionic equation. These guys that are canceled out, they have a special name. They are called spectator ions, coming from the fact that they just watch the reaction. They start off as ions, they end as ions. They don't really have a particular role that they play. So when we write an ionic equation, we exclude the spectator ions. So whatever is left is what our final answer will be. So down here, let me go ahead and write, I have the Ag ion, which is an important player, the NO3 ion, which is, oh, oops, my bad. All right, let me go back. I don't know how to go back and like change that, but let me go back and change that. Some of you on top of it kids may have noticed that I should have put NO3 here, NO3 minus 1, AQ here, and I should have crossed out the NO3s. All right, I don't know how to go back and redo that, so on this video without erasing all the work that I just did. So I'm just going to go back and start from the beginning. I'm sorry. So this becomes AgCl solid, and then my ions that are left over that don't do anything are the K positive and the NO3 minus, not the Cl minus. Sorry if I screwed that up. So you're going to cross out the K and the K, the NO3 and the NO3. So your final equation will be Ag positive AQ, which is this, plus your Cl minus AQ, and that will make your precipitate AgCl. So you're basically writing the two ions that go into making your precipitate. The other ones are going to be considered to be your spectator ions. Okay? These chemical equations are called net ionic equations. You write your reaction as usual. You write the solid being produced on the product side, and then you write the ions needed to make the solid on the reactant side in their aqueous ionic form. And then you balance. So let's take a look at this. We have lead nitrate, which is going to be PbNO3 2, and it's going to be AQ, plus ammonium sulfate, which is NH4 2 SO4 AQ, and it's going to do a double replacement where the Pb and the SO4 are going to mix together, and the NH4 and the NO3 are going to mix together. Pb's oxidation number is 2. The 2 came from here. SO4's is also 2. So when they drop and swap, it's just going to be Pb, SO4, and NH4, NO3. This is going to be aqueous because all nitrates are aqueous. And for PbSO4, you go to your solubility chart, you look up the sulfates. If you have yours out, it says all are soluble except Pb. That's all I need to know because that means that is my solid. Okay, so step 1 is to write out your equation as usual. Step 2 is now you are going to take your solid, PbSO4 solid, and then you are simply going to write the ions that make it up. So Pb is Pb plus 2, and SO4 is negative 2. Okay, you could go through the steps of writing out all the ions and then crossing out the spectators, but a shortcut is to simply find your precipitate and then go backwards and write the 2 ions that went into making that precipitate. And then if you needed to balance, you would, but this one is already balanced. All right, let's take a look at barium chloride. Barium chloride is BaCl2. And by the way, the word solution means that you are aqueous. Iron sulfate is FeSO4, and that's going to be AQ as well. Your product will be BaSO4 and FeCl. All right, let's take a look at the oxidation numbers. This is 2 and 2. Iron, you have to go to your red, white, and blue table. Iron's most common oxidation number is 3. So there's a 3 here and a 1 here. So when you drop and swap, these will cancel, and then the 3 and the 1 switch places, so it'll be FeCl3. All right, let's figure out which one is our precipitate. Go to your sulfates. For this guy, it says all are soluble except PbBa, so Ba is on that list. So that is our precipitate. And then FeCl3, the chlorides, all are soluble except Ag, Hg, Pb, and Cu. Iron's not on that list, so it's AQ. So then you take your precipitate, you write it as BaSO4 solid, and then the 2 ions that go into making it are Ba plus 2 and SO4 2 minus AQ. Now, for some reason, people don't do these ionic equations correctly. The word ionic means you're going to have ions. Look, those are your ions that you're going to write, and you're going to show how those ions go to form the precipitate in your equation. So for some reason, when we do this chapter and I test you on this, when it says write the ionic equation for whatever, I can't tell you how many people do not put these ions as part of the reactants, okay? It's telling you in the name that you're going to have ions in the equation. You write the ions that lead to the precipitate. And the ions are always going to be aqueous, okay? Because an ion means it's separated, and aqueous means that it's dissolved in water. So, all right, let's take a look at this one. So this one, the products are already written for you, so you don't have to do anything crazy to it. Here, you don't have a precipitate, you have a liquid. The liquids work the same way. Liquids are not aqueous. Liquids are actually water. It's not ions dissolved in water. Water is water. So it's going to work the same way. That water is going to be pulled out here. It's the unique thing that's happening. And then the 2 ions that go into making it are H positive and O2 minus. So then you would write it like that. Here, you do have to balance it. You have 2 hydrogens, so you need to put the 2 in front of there, and that's it. Okay. Here, in the second one, it gives you that the product, your precipitate, is CuOH2. So you can write that. And then the 2 ions that go into making it are Cu plus 2 AQ. Where did I get that plus 2 from? How was I able to look at this and like instantaneously know that the oxidation number of copper was a 2? Because of the dropped and swapped subscript. That 2 had to have started up there on copper. And then OH, always minus 1. And then you're going to put a 2 here to balance the hydroxides. Okay. If I asked you the spectator ions, you could look at this equation and see that sodium is aqueous here and sodium is aqueous here. So sodium, if you did that thing where you wrote them all out and canceled out the spectators, you would see that sodium does not change states of matter, so it stays aqueous. And you would also see that the SO4 is aqueous here and the SO4 is aqueous here. So if that question was asked, what are the spectator ions, you would see which ions stay aqueous on both sides of the equation. All right, what about a single replacement reaction? So in the previous problems, they were all double replacement. What happens if you have a single replacement reaction? So you have your solid magnesium plus copper sulfate, and you're going to make solid copper and magnesium sulfate AQ. You write the solutions as ions, cancel out the spectator ions that don't change, and rewrite it without the spectator ions. So let's see if I can fit all this. I have magnesium solid plus Cu plus 2AQ. How did I know that it was Cu plus 2 and not plus 1? Well, sulfate is always SO4 minus. So if it appears as a 1-to-1 ratio, it means that copper had to have a positive 2 oxidation number. And this is going to be AQ. To make solid copper, plus, I'm going to go down here, magnesium. Anything that says AQ is going to be rewritten in ionic aqueous form. I don't know what does that. AQ. Right. So then see where your spectator ions are. Magnesium is MgS here. It is Mg plus 2AQ. They are not the same thing. You can't cross those out. Copper is a solid here. It is aqueous here. These are not the same thing. They cannot get crossed out. SO4 2 minus AQ, though, is the same as SO4 2 minus over here. So these can get crossed out. So SO4 2 minus is your spectator ion, and then you will rewrite this with just the parts that remain. And notice it's usually the metal on one side, the aqueous ion on the other side, or vice versa, the aqueous ion on one side that goes to the metal on the other side. Okay. When you get good at this, you will eventually see that sulfate is aqueous here and sulfate's aqueous here. So eventually, if you get good at this, you probably don't need to write out all the ions like that, and you can just do it that way. But what you do need to be careful of is that you have to make sure you know what the oxidation number of copper would be when it's written as an ion, as well as the magnesium over here. All right, let's take a look at this. Potassium solid plus calcium hydroxide aqueous. Single replacement reaction. You're going to make potassium hydroxide plus calcium. Calcium is going to be a solid metal because in its room temperature state of matter, if you look at that colored periodic table, calcium is written in black, which means that it's a solid at room temperature. Potassium hydroxide, go to the solubility table. Solubility table says hydroxides are all insoluble except NaK, which means that it will be AQ. So here, we're going to write out all the ions. We're going to have K positive solid plus anything that is AQ gets split up into ions. And on the product side, KOH is aqueous, so we're going to go K positive AQ plus OH minus AQ plus Ca solid. Your spectator ion is hydroxide, and so your net ionic equation will be everything else that remains. And we will stop there for net ionic equations.